Oxymercuration of alkenes and the demercuration of these compounds as a way of synthesizing alcohols is another type of electrophilic addition that we're going to look at. The overall process is actually two separate reactions. First, an alkene is reacted with a mercury salt, most commonly a mercury acetate. This is a mercury in a +2 oxidation state. And then that compound is treated with a reducing agent, sodium borohydride. It's a sort of H-. The overall result is a Markovnikov addition of water across the double bond. And you might say, well, why use this to do that? For one thing, it involves mercury, which is a poisonous metal. And you can do direct hydration with water and acid. And the answer is that these conditions are considerably milder. They're non-acidic, and many organic compounds don't survive the acidic conditions for direct hydration. There's also no carbocation intermediate, and so there isn't a complication in these reactions with carbocation rearrangements. So if you look at the two examples that are shown here, you can see the overall hydration. Hydroxyl is added to the more substituted carbon, hydrogen to the less substituted in Markovnikov fashion, and we produce these alcohol final products. There's another example down here, hydroxyl added to the more substituted carbon. So same overall reaction pattern as direct hydration, just done under non-acidic conditions with no possibility of carbocation rearrangements. And that gives a hint to its mechanism. Before we go on to the mechanism, it's worth mentioning that these mercury salts are unusual things. They exist as an equilibrium between the diacetate, somewhat covalently bonded complex in this pair of ions where we have a mercuric acetate ion. And this is actually the reactive species in the reaction. So the mechanism here has something in common with the halonium ion mechanism that we saw with the reaction of halogens. So here's our overall reaction. We're only going to look at the mechanism of the reaction with mercury. The other mechanism is just a direct substitution by hydride. But what happens in these reactions is there's a complex formed between the alkene and mercury with the loss of one of the acetates. And that mercurinium ion forms a bridge in the same manner that halogen did in the halogenation reactions. You'll notice these are carried out in aqueous medium, and water, just like in halohydrogen formation, is abundant and a pretty good nucleophile. Also, like those reactions, it tends to add at the more substituted carbon because of the greater positive charge at that position. This opens up the mercurinium ion ring so that we end up with this oxonium ion and mercury on the other carbon. The oxonium ion is deprotonated in the usual fashion, and then sodium borohydride replaces the mercury with hydrogen in the compound. Stereochemistry of this reaction is also important. The bridging mercurinium ion means that the nucleophile, whether it's water or as an alcohol shown here, you could do this reaction in alcohols, here with methanol, that nucleophile has to attack from the backside of the mercurinium ion. So here the mercurinium ion is pointed away from us, so the methanol will attack from above. So we end up with the methanol pointed up, the mercury atom pointed down, leading to this intermediate. And then one final aspect of the stereochemistry is that the stereochemistry of the mercury is retained in this reduction reaction. And this can be observed by using isotopically labeled sodium borohydride, where we've replaced the hydrogen 1 with hydrogen 2 deuterium atoms. And you can see we end up with the deuterium retaining the stereochemistry of the hydrogen. You'll notice on the previous slide, we didn't go through the mechanism of that. It's a bit beyond the scope of this course. But the stereochemistry of this is certainly something we need to know. Another reaction that involves three-membered rings formed from alkenes is epoxidation of alkenes. And this is accomplished very simply in the lab by the reaction of alkenes with peroxy acids. Peroxycarboxylic acids have generic structures like you see here, where there's an additional oxygen beyond what you would see in a normal carboxylic acid. And that very weak peroxide bond leads to some interesting reactivity. It's a one-step reaction that leads to this bridging three-membered ring ether called an oxyrate or an epoxide. There are a host of peroxy acids that one can use in the laboratory, and a few of them are shown over here. So the relationship between a carboxylic acid and its peroxy derivative is shown here. Acetic acid, for instance, can be formed into peroxyacetic acid, and benzoic acid can be transformed into peroxybenzoic acid. These will all work in this reaction. So here we see peroxyacetic acid, and you'll notice that I've color-coded the oxygen so that we know which oxygen in this molecule is actually the one delivered to the alkene. And it turns out to be that's the terminal oxygen in these. So here's a simple example of that alkene transformed into an epoxide. This may seem like a low yield, but epoxides are very sensitive compounds because of the ring strain, and they're prone to undergoing nucleophilic ring opening, something we'll talk about a little bit later. So how do these peroxides form? And the answer is a concerted one-step mechanism. And that's shown here. It looks a little complex, but let's see if we can walk through it. So the reactive oxygen is that terminal oxygen that I color-coded on the previous slide. And if you want to think about this in a stepwise way, probably the best way is to start with the alkene, because in all of reactions we've seen before, this is acting as a nucleophile. And it's adding to this terminal oxygen. That causes the pair of electrons in the peroxide bond, these oxygen-oxygen single bonds are called peroxide bonds, to shift to this position, forming a new carbon-oxygen double bond. The pi bond from this existing carbonyl actually acts as a Bronsted base and deprotonates this hydrogen here from that terminal oxygen, and the pair of electrons that held it are the other pair of electrons that form the second bond in the ring. This is one step. All of those bond-making and bond-making processes happen at the same time. So one-step mechanism. The epoxide is going to retain whatever stereochemistry is present in the alkene. And what I mean by that is, if you look at these two examples, here we have a cis alkene, the methyl groups are cis, and those methyl groups will be cis on the newly formed ring. So if you think about the stereochemistry of these methyl groups with respect to the ring, they are cis. If the methyl groups are trans, then these methyl groups will retain that trans stereochemistry on the newly formed ring. This one would be formed in a racemic way. Also, I want to point out a very common reagent for carrying out these reactions is this compound you see here. It's Metachloroperoxybenzoic Acid, more commonly referred to by organic chemists as MCPBA. And the advantage of this over the peroxy acids that I showed you previously is, for one, this is a crystalline solid, very stable. You can keep it on the shelf. Many peroxy acids like peroxyacetic acid and peroxybenzoic acid are liquids at room temperature. This one makes this one easier to handle. It's easier to weigh out liquids for stoichiometry purposes. The other is that the byproduct of the reaction, this metachlorobenzoic acid, typically will precipitate out of dichloromethane. It's not soluble. And that's useful in purification process because we can simply filter off the precipitate and then evaporate the dichloromethane to isolate our product. Before we move on, it's worth mentioning that the formation of epoxides is a very important tool to organic chemists, and particularly synthetic organic chemists. And one of the reasons it's a powerful tool is that there have been developed over the years methods of synthesizing epoxides asymmetrically. What that refers to is the ability to selectively synthesize one enantiomer of two possible enantiomeric epoxide forms. This was pioneered by a chemist by the name of Cadbury Sharpless, who relatively recently won the Nobel Prize in part for this work. He used a rather complex mixture of a chiral tartaric ester, a titanium isoperoxide, a peroxy compound T-butyl peroxide as a reoxidant in dichloromethane. And he was able to synthesize chiral epoxides. And by switching out this tartaric ester to a different tartaric ester, you can steer this reaction to either enantiomeric form that you want. Extremely powerful tool in synthetic organic chemistry. We won't go into the mechanism of this, it's well beyond the scope of this course. So why make epoxides? And the answer is they're really quite useful. You can do many things with them. The strain inherent in that three-membered ring means they're prone to ring opening reactions. We're first going to look at acid catalyzed opening of epoxides. In this case, just with aqueous acid. And under these conditions, water will open the epoxide, and we end up producing 1,2-diols. These are historically referred to as glycols. And they invariably end up with an anti-stereochemistry. You can actually do this in one pot so that the epoxidation is occurring, and then as soon as the epoxide is formed, it immediately undergoes ring opening under acid catalysis. And that's kind of shown here where we're using peroxyacetic acid with water added. This peroxyacetic acid actually acts as the acid catalyst in this process. But the first thing that happens is formation of epoxide, and then we get a ring opening, and we would form, in this case, it forms a meso compound. And I'll leave it up to you to convince yourself that this is really a meso form. So how does it happen? We've seen a similar reaction before where acids react with ethers and they cause cleavage of the ethers. And that's essentially what's happening here. The acid is protonating the oxygen of the epoxide, and then we're getting a nucleophilic addition to one of the two carbons. And for reasons we discussed previously, that nucleophilic addition preferentially happens at the more substituted carbon because it bears more positive charge. This causes the ring to open, and the subsequent oxonium ion is deprotonated by additional water, and we end up with a 1,2-diol. So hopefully you recognize the pattern here that these three-membered ring intermediates in these reactions are prone to nucleophilic ring opening to give other intermediates or to give products that ultimately we isolate. It's worth looking a little more closely at the stereochemistry of that ring opening. So here we have an epoxide on a 5-membered ring, and we're looking kind of across the plane of the 5-membered ring, so the epoxide oxygen is pointed down from this perspective. In the presence of a catalytic amount of acid, that oxygen can be protonated, and once it is, then we have a good leaving group in the form of an alcohol functional group. So water can add, and this is an SN2 type process. So water being the nucleophile, it needs to donate that pair of electrons into the antibonding orbital of one of these carbon-oxygen bonds. And that means the stereochemical requirement is that it come from the opposite side of where the oxygen is. So that means when this bond is going to rupture, and we're going to form a new bond to the incoming water molecule pointed up. And so we end up with that hydroxyl pointed down and the oxygen pointing up. And we end up with these trans 1,2-diols. So we have some really powerful tool here. If we use peroxyacetic acid and acidic water, we end up with a glycol. But if we use other peroxy acids and non-nucleophilic solvents, like carbon tetrachloride or methylene chloride, we can isolate the intermediate epoxide. Very powerful synthetic tools. It turns out you can also open epoxides under basic conditions. And what's interesting about this reaction is that this is not a reaction that occurs with normal ethers. So normal ethers don't undergo nucleophilic kind of cleavage. So we can't use hydroxide, for instance, and kind of break apart a normal ether. And the reason for this is that there's no net energy gain. You're basically trading in an unstable anion for a different unstable anion. And they also tend to have rather high energy barriers to overcome. Epoxides, because of their ring strain in that three-membered ring, are far more prone to ring opening because you're relieving ring strain. And so hydroxide will add quite readily to one of the two carbons of the three-membered ring, has a very low activation energy, and we ultimately produce an alkoxide product, which is usually subsequently protonated. So here, more generically, is that reaction. So it looks very much the same as what we said before, but notice here in the arrow that we have base catalyst in here. We don't need a stoichiometric amount of base, we need a catalytic amount of base. And just like the acid catalyzed ring opening, we end up with the same products. We end up with these glycols, these 1,2-diols, and we also get the same stereochemical outcome because we're opening up that three-membered ring. This mechanism is simpler than the others because we have a very strong nucleophile present in the form of hydroxide. And that reaction is going to preferentially happen at the less substituted carbon because it's more SN2-like than the previous mechanism. And so there is this preference for opening at the less substituted carbon, opens the ring to produce an alkoxide. That will deprotonate water to give our glycol. Notice that in this step, we're regenerating the hydroxide catalyst. The important thing to remember about this, we get the same products, but this very first step, or the ring opening step, is happening at the less substituted carbon, and we can exploit that. There are nucleophiles related to hydroxide that will also open epoxides quite readily. So for instance, alkoxides of alcohol, such as sodium methoxide, is an excellent nucleophile, and it will open epoxides. It will also produce trans products, where the hydroxyl group is trans to the methoxy group. In this case, if you think about what's happening here, this methoxide can add to either carbon. We've only shown the product of addition to this lower carbon. If it adds to the upper carbon, we would produce the enantiomer. Other good nucleophiles. Ammonia, we've learned previously, is a good nucleophile in SN2 reactions. It will open epoxides. And if we do this in a protic solvent, then the resulting alkoxide gets protonated. Opening epoxides with really strong nucleophiles is also an important synthetic tool. And this is very important because it allows us to make carbon-carbon bonds quite readily. And some of the most important nucleophiles that we've already discussed are organometallics, such as Grignard reagents and organolithiums. These are extremely powerful nucleophiles. So if we take an epoxide and we treat it with one of these, and then follow that up by quenching the reaction with a little aqueous acid to protonate the resulting alkoxide, we're going to form new alcohols and a newly formed carbon-carbon bond in the structure. And so we're able to build bigger structures out of smaller pieces. And this is a very important synthetic tool. Whenever you can make carbon-carbon bonds, then you're building bigger molecules out of smaller ones. And that's a real fundamental, important thing to do in synthetic chemistry. So a couple of real-world examples. So the carbon that the lithium is attached to is the nucleophile. And because this is a basic ring opening, it's going to open at the less substituted carbon. It's going to break this bond here. The resulting alkoxide is then subsequently protonated by adding aqueous acid. You'll notice the two arrows here, the two arrows indicating these are two discrete reactions done separately. And that should make sense because you know by now that you cannot have water present when you're using an organometallic reagent. So this first step in the process has to be done under strictly anhydrous conditions. But once that reaction has gone to completion, we can then add our aqueous acid to the mixture to protonate the alkoxide. This second example is worth looking at. Nucleophilic carbon is the one attached to the magnesium, and so that nucleophilic carbon is adding to the less substituted carbon of our epoxide. Here's our newly formed carbon-carbon bond, and then the alkoxide produced by that ring opening is protonated by the water. You can also open epoxides with hydride, H-, and that's an interesting thing to think about because you're simply adding another hydrogen to the molecule. And this is also a reaction that's going to be regioselective. The addition of that hydride is going to be the less substituted carbon of the epoxide. So here we have a secondary carbon and a tertiary carbon. The hydride is selectively delivered to the secondary carbon. So there's that new hydride. And if we could isotopically label it, we would discover that it would have an anti-relationship to the resulting alcohol in our final product. So this is another one of those two-step reactions. Lithium aluminum hydride is incompatible with water, and so it has to be reacted under anhydrous conditions. Once those reactions are complete and the alkoxide is formed, we then add acid to protonate those alkoxides. And lastly, there's a variation on the organometallic reagents that is very, very commonly used because it gives such good yields. And these are what are known as organocuprates. Organocuprates are made from organolithiums, so you previously have to make organolithium that is reacted with copper cyanide. And that reaction produces these kind of complex stoichiometrically compounds where we have a copper metal bonded to these groups. And it changes their reactivity in some very important ways. But one of the things we need to know from a reactions point of view is it just makes them much better, more selective nucleophiles for ring opening, that ring opening is still happening selectively at the less substituted carbon of the epoxide. And you can see that in that second example down here, where the predominant product is the addition of this butyl group to the less substituted carbon. There's the butyl group that we've added.